So attention everyone, let's finally do it. Decision regions with two inputs, okay? So we have a neural network with 3 hidden layers and we are using ReLU as an activation function. We talked about ReLU activations, okay? So there are 2 inputs, x1 and x2, because that's the best we can do to visualize. The moment it becomes 3 inputs, it becomes very hard to visualize. And then I have 3 hidden neurons, and then finally the output. And let's say, so how do the decision regions look like? When we talk about logistic, we said that decision region is a straight line. In general, it's a hyperplane. Right? That you can visualize. But now if you have 3 hidden units, then what happens? So let's try to go over it. So we have x1 and x2, they are getting weighed by this, the first level weights, w1 and b1, these are vectors, or these are matrices. W1 is a matrix. What's the size of w1? 2 cross 3. And b1? So w1 is r2 cross 3 and b1 is r3 cross 1, and then you get, w times x will give you h, and wx plus b will give you z1, and then you apply the activation function, you get the output, which is a1. Right? So a1 is, what's the size of a1? The output of the hidden layer, 3. Right? There are 3 hidden units. What's the size of w2? 3 cross 1, and b is just a real. Right? b2 is a real number. Okay. How do we compute? z1 is this term, the weighted sum of x1 and x2 plus a bias term, and a1 becomes h, that activation function, sigmoid function applied to z11. Similarly, z2 is given by these weight matrices, these weights, and plus the bias term. This is the second component of the bias term, and similarly z3 is the third component. Okay. And in the last layer, we get again z is before the activation is applied, and which will be given by a1, which is output of the hidden layer, times w21, the first weight, and a2, w22, and so on. This is clear? Okay. So if you look at it carefully, let's look at z1. How does it look like? So here we have z1. It is a linear combination of x1 and x2. So here let's say I look at x2, and this is my x1. Okay? This is my x2. And I am representing my z11, this term, as the color in this picture, because I have to see how it varies with the inputs, 2 inputs. So I have to represent the value as a color. You can think of it, the lighter the color, the higher the value is. Or if you want to visualize in 3-dimensional, just think of it, this thing is popping out, as the color is becoming lighter. So that's the 3rd dimension, which is the value of z1. This clear? Now we want to find the decision boundaries. So I'll put some threshold. I'll say that, my decision region is that if this particular function is equal to a threshold, is less than equal to a threshold, then it's class 0. It's greater than a threshold, it's class 1. And the decision boundary is when it is equal to threshold. So let's look at the, points where z1 is a constant value. So in other terms, I look at this picture here, and here the color represents the value of z1. So wherever the color is the same, that is a constant value for the z. And these lines, they are representing those points which have the same color. So different lines here represent different values of z's. And you can see it is kind of increasing in this direction perpendicular to z. So here in this direction, z is increasing because it's getting lighter and lighter. And along this direction, z is the same along this line. Is it clear? This visualization is clear? Okay. Now this is a linear function of x1 and x2. So my, the point where Z11 is constant would be a straight line, because you will equate this to a constant, and when this term is equal to a constant, that would be just a hyperplane. So all these lines here would represent the points where Z is constant. So that's the story for Z11. I have a similar story for Z12, the second hidden unit, the input to the second hidden unit, except that these weights may be different. So these lines that give you the same value of Z, their slopes may be different. And the gradient along the line, so when you go perpendicular to these lines, the rate at which your Z will increase, they may also be different. And the baseline value may also be different. So you see, this is a darker shade here. So here probably the baseline is smaller. And these are the lines where Z is constant and then it is increasing in this direction. Okay? And similarly, I can draw Z3, the third hidden unit, and it's behaving like this. Okay? Yeah.
How you concluded baseline is smaller?
Because this is darker. So if I put x equal to 0, x1 and x2 equal to 0, maybe I'll get to this point. And then the color here is representing the value of B12. And here if I put x1, x2 equal to 0, color here is representing B11. And I can see this is lighter than this color here. So the baseline is smaller here. Similarly, I can visualize Z13. Now when I apply the activation on top of these, I get A11, which is h of Z11. And this activation function is the ReLU activation function. So anything greater than 0, it passes on. Anything less than 0, it makes it equal to 0. So let's say this is the line when Z equal to 0. So greater than 0, we have something, things as before. But less than 0, I have made it all zeros. So this is how it will look. My output as a function of input, my A1 as a function of x1 and x2 after my ReLU layer, after my activations. Same I can do for this one, for the second neuron. And here maybe the line of 0 is something like this. So left of this is all blank with the same color, which means Z is not changing if x1 and x2 is changing in this region. And here it is increasing. Right? So that's the direction of increase of Z. And this is the direction of Z equal to constant along these lines. Okay? And similarly, I can think of a third neuron and, the activation functions like that. Okay? This is clear?
Yes.
Now we add these two. We add these two in the second layer with some weights, and we add another bias term here. So what happens? I apply a weight to the activation of the first neuron. And the weight could be positive, negative, it could be small, it could be large. And depending upon the weight, you see, here these lines are a bit far away, but here the lines are closer. So this probably implies that this W22 is greater than 1. Because now these lines correspond to the same lines here. So the intensity is actually increasing faster along these lines. So I've scaled these numbers more. Right? Here I see the distance is slightly more. So maybe this W21 is less than 1. And here again distance is increased. So W13 is less than 1. So this is after scaling. Now I add them up. So after the scaling, I add a bias. So this is how, if I add these three curves and the intensities, this is how something in the output might look like. And you see, all the lines here correspond to the points where your output is the same value. Because this is the region where, if you look at a point here, let's call this, let's say, region number 1. Okay? What is happening in region number 1? So this is region number 1. So this activation is actually 0. And if I look at region number 1 here, the first activation is active. The Z corresponding to that is positive. So this is going to behave like increasing or increasing in this direction. I'm sorry, I think the colors are a bit messed up here. Increasing in this direction and constant in this direction. Okay? And here if I look at region number 1, this is also 0. So in this region, only Z1 is contributing. So the graph or the picture that you will get, it will be very similar to this region here. Okay? Similarly, if I look at region number 2 here, region number 2. So this is region number 2, region number 2, region number 2. All three are active. All three have, Zi is corresponding to greater than 0. So I'll get a change in the slope, and maybe it will look something like this. So now, if I want to look at a decision boundary, I have to trace a line here, which is again linear in this region. It will be hyperplane in higher dimensions. But the moment it touches this line, what is happening? Another unit is getting activated. So the slope of this line is going to change here. So this z is same, this z is same, and then again it hits another unit, which becomes inactive. Right? So this unit here becomes inactive. So the slope again changes. So this line represents the region where z is constant. And if I want to look at regions where z is less than this threshold, maybe that is the region. And z greater than threshold is the other side of this region. Right? So you can trace all these lines which have the constant value of z, and points on one side of this line will be one decision region, points on the other side of that contour would be the other decision region. And you can see that the decision region could be very complicated. So for example, I look at here, I trace a point here. Yeah, so let's say, yeah, I start with this guy, it comes here, it goes here, and from here it goes like this, and then it goes like this. So you see, it's a highly nonlinear kind of a region. So all the points greater than, this value may be here, and all the points less than this value may be in this side of this thing. So we see with just 3 neurons and just one hidden layer, I have increased the complexity of my decision regions quite significantly. And last time we saw that, just with one hidden unit I can represent any function to arbitrary degree of accuracy. So similar results also in the classification sense are there, that they are in some sense universal approximators. But the thing that is still open is sort of number of units that you will need to represent different types of regions. And it turns out as you go deeper, you would need lesser units to represent the same complexity. Here you might need exponential units for certain kinds, like XOR, not XOR, but certain kinds of functions. Okay, so this is as far as we can go to visualize neural networks, but in general when we are at deep networks, then it becomes very hard to visualize. And there are maybe other methods to look at this in a slightly different manner. But we'll stop here and we'll come to how to learn neural networks. And I would apologize to those who have done this course before, neural networks course. For them it may be a little bit of repetition. And also apologies to those who are doing it for the first time, because for them it may be very fast. So I guess both these groups have to bear with me. I'll try to do it fast, but those who can't catch up, they have to look at the notes and just pick it on their own. Okay. I want to move to RNNs and LSTMs very quickly. But yeah. So that's a general architecture of a 3-layered, shallow neural network. Right? It has an input layer and a hidden layer and the output layer. And then this is the loss function, which is computed on the outputs. Okay. So this we looked at last time, that how to go from input to output. But let's sort of look at a more general neural network. Let's say it has D layers. Instead of just 3 layers, it has these D layers. Okay. So I have the input here, again m-dimensional feature vector. I can also represent it as z of 0. So the input to every layer is represented by z. Output of that layer is represented by the A's. Okay. So the output here would be A1. And they are combined with the weights and the biases to get the input to the next layer, which will become Z2. And then this will give me the output of A2 from here to here. Okay. And this we can say that this has M0 equal to M, the size of a feature vector. And then finally at the last layer, I can write it as zd plus 1 and also as y hat, which is my final output of the neural network. This is clear? So if I have a regression problem, I'll just look at the least square. I'll subtract y from y hat, and then maybe, this will be only a single dimensional number. So in this case, the k would be equal to 1, or m of d plus 1 equal to 1 for regression problems. For k class classification problems, this would be equal to k. And then we apply the cross entropy or the least squared error loss, and we minimize this. Okay. So now can somebody help me write the formulas from how do we compute these weights or the inputs and the outputs of these layers? And quickly. If you use matrix notation, it becomes really, really simple.
So Z at layer L
Yeah.
is equal to omega at layer L.
Okay.
Into A at layer L minus 1 plus B at layer L.
Exactly, fine. So Z at layer L, I'm representing, and I can also subscript with an I, representing the examples, example number I, but we can omit it also. We are going to use both the notations, separately. And dot represents, it's a column vector. Right? At layer L is W at L transpose times A at L minus 1 plus the bias B at L. Okay? Thank you. What is the output? A of L is just H, the activation function, either sigmoid or ReLU, whatever you have, applied to Z of L. And here this function, so Z of L, I, is a vector, right? So Z, what's the size of this vector? We are saying that at layer M, my size is ML, right? So it's a vector of size L. And I apply a function to this vector. So what is my notation here mean? That I apply this function to every component of that vector independently. I get the vector of the same size. So my AIL will also be a vector of the same size. And this H function I am applying to each component separately. In general, you can have many other functions which can look at multiple components together, do something with it. But here it is just each function, you are applying that function separately.
So does the dot, subscript I and I refer to just that specific example of my training set?
That's right. I represent a specific example. The reason I'm writing like this is I can, just convert it to a matrix notation now. If I look at all the examples, I can just omit I, and I can represent the Z with a capital Z representing the full matrix. So the whole equation of the neural network actually becomes a matrix vector product or the matrix product. This is what is called forward propagation. So what is forward propagation? I am looking at the input. Here I am applying the weights, applying the bias, and then computing the input to the first hidden layer, then applying the activation function, getting the first output at the first hidden layer. And then I repeat this process for each layer until the last layer. So I'm forward propagating. I'm propagating my input, which is xi, layer by layer until I reach the final layer, which will give me the yi hat. So that is why it is called forward propagation. What are my model parameters? Weights and biases at every layer. And how many weights I have? WL and BL. WL is matrix. And what's the size of the matrix? ML minus 1 cross ML. Because there are ML minus 1, input size, and the output side is ML. And, the product of these two is the size of this matrix. Bias is M times L, M subscript L. So, this is how this get. You think of it, if you have a deep network with, lots of hidden units, my parameters are quadratic in the number of, parameters here. So there's anyway very big, very large number of parameters. Okay. I can also, when I'm doing this forward propagation, I can propagate one example, I can propagate all the example at once, or I can propagate what is called a mini batch of examples. So we'll talk about it when we talk about mini batch gradient descent. So instead of looking at all examples, I can look at a subset of examples. And for that subset of examples, I can represent them in xit, where I belongs to a subset. Right? So instead of looking at all the n examples, I'm looking at, let's say, maybe n by 10 examples, right? 1/10 of the examples. I look at this, and correspondingly I can have a z. So again, I can represent that forward propagation for that mini batch in the matrix vectors format, right? Matrices. And these can be very fast implemented on the GPUs. And that is what, that's why the GPUs have been extremely successful or extremely useful for, learning these networks very quickly. Because you look at this, these are basically matrix into matrix operations, if I'm propagating a bunch of examples. And matrix product is how much time does it take? If I have n cross n matrix, I'm multiplying it with n cross n matrix, I'll take n cube time, right? So it's anyway a lot of time, a lot of computation that goes on. But it turns out that these operations have a lot of what is called locality of reference. Typically my CPUs are very fast, my GPUs are very fast. Access to memory is very slow. So they have a lot of locality of reference, so you don't have to keep because same element you access multiple times to do the products. So when you use, for example, SciPy, NumPys, or if you use CUDA-Py, is it called CUDA-Py? Huh? NVIDIA, there is a library, right? Python library that connects these operations. What is it called? Huh? There's some Py. Huh? No, not PyTorch. This is the BLAS library, which is CUDA equivalent to BLAS. CuBLAS or QBLAS. CuBLAS. So yeah, so that library basically, what you need from that library is these matrix products. And when you call that library to do the matrix products, it's very, very fast. So I will just leave it as a homework exercise. Okay. Try computing gigaflops. What is gigaflops? Giga floating point operations per second that your program can do. Okay? So you're going to, in matrix multiply. So you're trying to multiply two matrices, right? And the matrix size has to be large. Can't be like, 2 cross 2 matrix, right? It has to be 1,000 cross 1,000 at least. So 1,000 cross 1,000 matrix, n is 1,000. So matrix multiplication will take n cube, so 10 to the power 9, which is like a billion. Right? If you have a gigaflops system, then it will happen in about a second's time. So which is still okay. Maybe you can do 5,000 cross 5,000 cross 5,000. Then it will take about, if it's a gigaflop, it will take about 125 seconds. You have to get the size right. Well, how are you going to matrix multiply? A Python loop. Okay, just write for I equal to 1 to n, for j equal to 1 to n, for k equal to 1 to n, whatever, right? And then do the matrix multiply. What is the second thing you are going to do? Huh? No. NumPy. NumPy has it or SciPy have it? NumPy has a matrix multiplication? SciPy, what does SciPy have then? Huh? Just check. Maybe this will be NumPy. If SciPy has a different matrix multiplication, you should check that. Right? Check both of them out. Huh? Both have. So just try both of them separately then. This is B1 and this is B2. Try NumPy, SciPy. And then third is CuPy, CUDA-Py. Right? So you can try it on a laptop or wherever you have, a GPU. And then maybe you guys know C programming. It's a very simple code. It's a good idea. Right? So 3 loops in a C program, right? You can generate the matrices randomly and use the time routine, right? So if you have 1,000 cross 1,000 matrices, you know exactly how many floating point operations you are doing. It's actually 2 into 1,000 cube minus something, right? Because there's addition and multiplication. So multiplications are exactly n cube. Additions are like little less than n cube. So you can calculate exactly the number of operations. Put a timer in the beginning, timer in the end. Only when you are doing the matrix multiply, not when you are generating the matrix. When you are generating, generate it randomly. And put it something there so that it's in the cache also, so you don't have to worry about the cache timing. Put the matrix multiply in a loop, run it 10 times, and then divide your total numbers by 10 so that if there are any caching effects, they are no longer there. And you will be surprised to see the performance numbers here. Right? So I'll keep that as a suspense for you. You run it, you see how it. Maybe plot as a function of n, which is the matrix size. Right? And then we are going to run it 10 times. I'll say run it 30 times. Because 30 is a good enough number. So you can calculate the mean gigaflops and you can also calculate the standard deviation of the gigaflops. So whenever you are doing this scientific plotting, you always put the error bars. So run, let's say 30 times in a loop. And then plot mean plus minus standard deviation gigaflops. Okay? So you have these plots where you plot this x, f of x, right? You have this, and then you plot the error bars here, right? Which is mean plus minus, let's say, standard deviation. These plots. Should I make it a graded homework?
Yes.
Huh? Only one person, two people are saying. You don't want to do it? It's a good exercise. It's a good. Okay, right now let me keep it ungraded. I'll ask you next time. Depending upon your responses, we'll see whether to make it graded or not. Okay? This is the heart of, this is why NVIDIA is there where it is today, right? Like what? How many? $500 billion valuations?
4 trillion now.
4 trillion now? Wow. This is why it is, right? Matrix multiplication. They just were able to do that very quickly, very fast on these things. Right? So this is an exercise worth doing. Okay. So that is what is happening essentially, right? So your matrix multiplications, you're getting from input to output. How do we learn the networks? How do we go from, optimizing the weights? So when you get an output, there's a loss function you want to do. So we looked at, different types of loss functions for, classification problems. For regression also we discussed different types of loss functions. Essentially a function of y and y hat. Y is the label for that example and y hat is the predicted label for that example. And then you apply some function. It's a multi-class classification problem. You'll look at what's called a cross-entropy loss. Logistic regression, you will just look at the logistic optimization, which is again a special case of cross-entropy. For regression, you do a squared error, you can do L1 error, do L4 error, various metrics you can use. But essentially, as what you are doing in these neural networks is minimizing this loss function by finding the parameters W and B, which gives you the minimum loss on your training data. Right? So your optimal model, and these models that you see, right, LLMA 70B, it is just these W stars and B stars that the model has learned. Right? Except that the network is deep, there are many parameters, and there are other types of weights, convolutional weights, this, that, we'll talk about that. But essentially, in sum, that is the only thing that is happening. Okay? So the question is, how do we learn these model parameters? How do we optimize this? Unlike in the least square case, in the general simple regression, I could just take a derivative and set it equal to 0. It's a nice convex function. I can optimize. I'll get this optimal output. But here my function, as we just saw, is highly non-convex, highly non-linear, and it is totally unimaginable. It can approximate any function that I have given to it. It can create any decision boundaries I like. Such a complicated function. And then how do I optimize that function? And that is what many people do for their bread and butter, right? It's like, if you know this, you can sort of I'll tell you. So you can, if you optimize a learning algorithm by a factor of 2, how much money you have saved? Because these trainings take hundreds of GPUs clusters for about 6 months for these large language model training, right? For 6 months they run it. That's a lot of money. And if you just by algorithmic improvement, if you can just do it 2x, then you have saved half of the hardware cost. So and electricity cost as well. So yeah, it's a very important problem. Okay. Intractable, very complex function, highly non-convex, can only find a local minima. That's the best we do in machine learning. We find the gradient with respect to W and B and then move in the direction of negative gradient. And then there are various optimizations that we do to sort of, minimize the loss. Okay, that's fine. So, how do we find the gradient? Right? I've told you what the function looks like. I've told you how to do the forward propagation. How do I get from x to y hat? Now, you have to find me the gradient. So, we'll take a 2-minute break. And because get ready, because that's going to be a little heavy. Okay? So, yeah, your attention is required. 100% attention is needed. So, we'll just pause here. So, we are discussing backpropagation and chain rule for vector valued functions. Okay? Any questions on what we discussed last time? Okay, so if we have two functions, h, which is composition of f and g, we want to find the gradient of h with respect to the input x. What do? We find the gradient of f with respect to g of x and then find the gradient of g and just take the matrix product. Then you get the gradient of h with respect to x. And this works for all the cases. Okay? Let's try to understand, this part is clear? We thought about it? Any comments on this? Nobody thought about it, huh? Okay. So, today I'm just going to very quickly look at a special case where your h is from M2 to R1 or your f is M2 to R1. So, think of f as your loss function and then g as the activation functions at different layers. Okay. Now we want to just visualize what does it mean, So what will be the gradient of h of x? Is the gradient of f at g of x times the gradient of g of x at x. Okay. Yeah. Yeah, this is the connector is, this cable is pathetic. Let me call them. हेलो LH510 में प्रोजेक्टर प्रॉब्लम आ रही है. हाँ. Okay. So what is my function f? F is mapping from M2 to a real number. Okay. And what is G doing? M1 to M2. So yeah, let's look at this. So this is h of x, I can think of it as f of g of x. Okay. Now what is this f doing? It's taking a vector input. So I can write it as f of g1. Okay. And what is g1 taking? It's also taking a vector input. So x1, x2, all the way till x. G is m1, right? So m1 dimensional vector. And the second component is g2. x1, x2, all the way till x m1. And all the way till g of, what is g? It's mapping from m1 to m2, right? So it's an m2 dimensional vector. x1, x2, all the way till x m1. Now we look at the gradient of f. The gradient of f will be, हाँ ये ठीक नहीं आ रहा है, बार बार डिस्कनेक्ट हो जाता है, नॉइज आ रही है बहुत ज़्यादा.
हाँ सर, ये
केबल में प्रॉब्लम है.
हाँ केबल का हो सकता है. चेंज करते हैं केबल.
So the gradient of f, what will be the size of the gradient of f? It will map an m2 dimensional vector to m1 dimensional vector, right? Okay. So what does this mean? I'm sorry, f of x. F of x is, no, wait. What is f? Okay, that's fine. So f has these m2 components, right? It's taking the m2 components as input and it's mapping onto a real number, right? So if I take the gradient, I'll take the gradient with respect to each of those components. So let's look at it a little more carefully. Here, so what are the sizes? H of x is mapping from m2 to r1. So what will be the gradient of h of x? It will map from m2 to m2. F is mapping from m2 to r1. So this will also map m2 to m2. And the gradient of g would be so this would be r m1. It will map it to r m2 cross m1. But these products of these two terms, what will the product become? This will become, so this is M2 cross M1, this is M2. So this will become M1. There's a mistake somewhere, no? H would be from R M2 to R. H would be R M1. Yeah, that's a mistake. Right? This is R M1 because X is the size M1. Right? Yeah. So this will become R M1. This is clear? Okay. So. Yeah, so gradient of F would become M2 to M1. And gradient of G would become R M1 to R M2 cross M1. Okay. So if you look at these product, right? So what is of this derivative of H with respect to X? It will be the delta F times delta G. So I can write this as, so let's say I look at delta of F by delta of Xj, right? Or actually let me do delta of H. This is, yes. I want to differentiate H with respect to the jth component of X. So this will be I differentiate this F, I think of it F as a function of U. I differentiate it with the ith component and I sum it. Into, I look at del G, or rather del Ui, del Xj. Okay. So what am I doing? So that's my H. I'm taking the derivative with respect to a particular component of F. I want to find this derivative of with respect to a particular component xi. Okay. Now each of the input of x, g1, g2, they are all dependent on xi. So what do? I take the partial derivative of x with respect to a particular component uj and take the derivative of that component uj with respect to xi, and I sum it across all such components. That is essentially my derivative of h with respect to xi. So that's the chain rule. So unlike in the single valued function where you can just take the partial derivatives and multiply that. Now if you take the derivatives, you can affect the change in f or affect the change in H through multiple paths. If xi changes, it affects the change in H through change in G1 as well as through change in G2 as well as through change in GM2. So all of these change. So we look at each of those changes separately, and if we just add that up, because my deltas are going to be very small, that will essentially going to give me the complete change. So that's the intuition behind the chain rule for the matrix derivatives. For the vector valued functions. Is this clear? Okay, fine.
Sir,
Yeah.
sir, if we are taking all the components of G,
Yeah.
what is the meaning of UJ then?
No. So basically, just a notation. So for example, f is a function. It's a function of m2 variables, right? And each of those m2 variables are functions of all the x's, which are m1 variables. So I take the derivative of h with respect to the jth component, uj. I'm just representing the jth component as gj as uj, just for simplicity of notation. And then with respect to uj, I take the derivative of uj with respect to xi, or xi. And then I sum it across. Okay? Fine. So, yes, so how do we do backpropagation in neural networks now? Now we have all the machinery to actually compute the backpropagation, and it turns out to be a very simple formula. So I have these inputs x1 to xm. We can call it z0, z superscript 0. Through the first hidden layer, I get m1 units, and I get an output which is a1, and then it gets fed into the next layer through w superscript 2's, and I get an output which is a2, and so on, all the way till the final, and then here I combine them to get my loss function. Right? And to learn these networks, I want to compute this derivative with respect to all the weights and all the biases. And now that I have done the chain rule for vector valued functions, I can think of it as a vector valued functions. Each layer I can think of it as a vector function. It's taking a vector of size mi, or mj, and giving an output of size mj plus 1. And then I can apply the derivatives, and so let's try to work that out. I mean, have you guys worked that out, or should we just quickly work it out in the class? Is it boring? We can skip it, you can just give it, or should we just work it out? Huh? Work it out? Okay, let's try to quickly work it out. Okay, fine. So what's your loss function? We want to view loss as a function of weights and the biases. And these weights and W and B represent weights and biases at all the layers. Okay? And I can sum over all the examples, 1 to n. My first function, which is yi and yi hat, and some function of that, right? If it's a regression problem, it will be a squared loss. If it's a classification problem, then I can have a cross entropy loss. And this yi hat is essentially a function of the activation at the last layer. So ai, and here I put a dot, which means it's a vector, at the d plus 1, which is my last layer. Okay? So, if I want to find the derivative of my loss with respect to w and b, I can find the derivative of my loss. So this loss is a real number, right? So what's the size of the loss function? It's mapping a vector of size. What size? Huh? Come on, you have to participate. What size? You'll get the notations. Right? So first layer has m1 units, second layer has m2 units, and so on. And the last layer is how many units? M to the md minus 1, md plus 1. So what will we be mapping it to? From md plus 1 to a real number. Loss is always a real number. Okay? So if I take the derivative of this with respect to AIs, so basically it is sum over all the examples. So I can consider one example at a time and find the derivative with respect to that example, and I'll sum it up because derivative would be additive because it's sum of all the derivatives. So I can take the derivative with respect to AI. So this will become a vector of size m to the md plus 1. That will be the vector of size md plus 1. Okay? Now what is AID plus 1? Output is activation applied to ZI, the input at D plus 1. This activation could be a ReLU activation, could be a sigmoid, I can take any activation. But, so if you think of this function H, it's mapping Rmd plus 1 to Rmd plus 1. So its derivative would be a matrix in general. But this is a very special function. What does it do? If I look at this function, I have a vector and I'm applying H to it. So, and then it gives you a vector of the same size. So it applies H to this and gives me this output. It applies H to the same component and gives me this output, and so on. It applies H to the third component and gives me the third output. So the first output here, it only depends on the first input here. The first output here only depends on the first input, does not depend on all the other inputs. So in general, its derivative would be a matrix, but if I differentiate this with respect to these components, I'll get a 0. So basically, I'll only get the diagonal components in this matrix. So, yeah. So essentially, what will be my derivative? So del of A with respect to del of Z, what will that be? I can put the superscript and subscript suitably, but at each layer this will be true. This will be a diagonal matrix of H of Z if it is a simple, that sigmoid type activation function, and 1 minus H of Z. And what do I mean by diagonal here? And Z is a vector. So then, just look at the first component here, put it in the first component diagonal, and so on. So this would be essentially H of Z1, 1 minus H of Z1. And then this will be all zeros, here all zeros. Next will be H of Z2, 1 minus H of Z2, and so on. And all the other components will be 0. Okay, so this is simple. This differentiation is simple. Now, what is the input at the D plus first layer? It is the weight at D plus 1 times AI, the output of the previous layer, AID, plus the bias. Right? So now this is mapping a function of size MD to MD plus 1. So its derivative would be a full matrix. Okay. Okay. So how do I find? Now I need to kind of, find the derivative of output, this output which I lost, with respect to my weights. So I have to find this derivative with respect to these weights, W's and B's at the D plus first layer. But I have to also find the derivative of output with respect to weights of the previous layers. So therefore, and they influence through AID. So what do I have? Yeah. So basically, I also need to compute the derivative of this loss with respect to AID, so that I can compute the derivative of loss with respect to the weights in the previous layer. And I keep doing that for each layer going back. So that's essentially the backpropagation. 3 things I need to compute. I need to compute the derivative of loss with respect to the last layer. I need to compute the derivative of the output of a layer with respect to the output of the previous layer. And then for every layer, I have to find the derivative with respect to the weight functions. Once I've done these 3, then I'm done. Because all these are matrix functions, matrix derivatives, I can simply multiply them according to the chain rule that we just figured out. And then we can just find the rate of change of the loss function with respect to the weights and biases at different layers. Okay, so what about the first one? This is standard, cross entropy loss. So this I think we can do. So we don't have to spend too much time on this one. Let's look at the second term here, which is the derivative of AI with respect to AI minus 1 and AI with respect to the weights at that layer. Okay. So what's the formula for AI L? Yeah, so can somebody help me write this formula? AI L equal to Hmm? H of ZIL, okay. Let me drop the subscript I, it's kind of understood. So, yeah. So, or anyways, let's see. Yeah. So, ZIL is what? WL transpose AI L minus 1 plus BL. Okay. So this I have already discussed. This would be a diagonal. So I need to find del of ZIL with respect to del of AI L minus 1. Okay. Yep. So let's look at a particular component. Let's look at a jth component here and look at, or let me not use j, let me just call it uth component and with respect to the vth component here. Okay. So I want to find, okay, let me write it more legibly. Del Z at layer L UI and with respect to del A L minus 1 V I. Right? This will be, let's say this is a matrix M. So this would be, M is a bad name. Okay, so what should I use here? Z Y X U T Q. Let's call it Q. So this would be which component of Q? So I am finding derivative of AL with derivative of ZL with respect to derivative of AL minus 1, and let's say this is a matrix Q, right? So this would be which component? No, this would be which component of Q? I'm looking at U in the numerator, derivative of the uth component of Z. So the components make the indices of the columns. So the components make the indices of the rows. So this will be Q, U, V. Okay? And V is the thing through which we are derivating. That makes the indices of the columns. Okay? Yeah. So what this would be? So what is ZUI? ZUI. This you should be able to do quickly, no? Tell me. You guys are much better at me for doing these things. Matrix vector product. Okay, we need a break. Let's wake up. Let's do a mindfulness break for. Huh? Summation. Okay, tell me summation over.
WL transpose.
No, I want to write it in individual terms.
Yeah, there will be WL transpose term of J.
Yeah, but there will be no transpose. If all the entries are scalar now, I'm opening it up, writing it as a summation. So what is the index of the summation? Huh?
WLJU.
WLJU. And summation is over?
Summation will be over J.
J is going from 1 to?
N.
Huh? Which M? Which M? Huh?
So the row dimension,
Yeah.
the row dimension of AI.
Which is? Let's go back to this picture. Yeah, so we are looking at the L minus 1th. So what will it be? How many units? M of L minus 1, right? So this is going from M to, this is M L minus 1. Okay? Now what?
Into
A, A, J, I, L minus 1 plus B, yeah, which one? U? U. Maybe I should have given you this as a quiz. Then you'll all wake up. Okay, fine. So this is ZUI. Now I want to find its derivative with respect to AVI. So del ZUI L with respect to del A L minus 1 VI. So if you look at J, if J is not equal to V, then this term B is not dependent on ALVI. So derivative with respect to B will be 0. This is only dependent on ALVI only when J equal to V. All the other terms are 0. And then it's a linear relationship. So what do I get? W L V U. Okay? So I get Q U V equal to W L V U, or in other words Q equal to W L transpose. Right? So this I get the derivative of Z with respect to A, and I have already calculated derivative of A with respect to Z. So what is the derivative of AI AL with respect to AL minus 1? AI diagonal H of Z L 1 minus H of Z L times derivative of Z with respect to AL, which is WL transpose. It really becomes simple. Just a matrix product. Okay? And these are just scaling of the, if you multiply diagonal matrix with the matrix, what happens? If you pre-multiply a diagonal matrix with the matrix, you are scaling the rows of the matrices. If you post-multiply, then you are scaling the columns. Is it? Yeah. So, no, wait. No. You are scaling the columns. D into matrix M. What does it do if it's a diagonal matrix?
Scaling each column by the DI, right?
So what will happen? You multiply this with this, you get the first column.
So, but all are 0, right?
This is 0, this is 0.
Yeah, so we
So let's say it's M dot 1, M dot 2, and so on. M dot 3. Okay? So this would be
entry is scaling every row, ith.
every row?
Ith entry of diagonal is scaling every ith row.
Okay. So it's scaling every row. Yeah. Okay, fine. So we have calculated the derivative with respect to A. Now, how about calculating derivative of A with respect to weights and biases? Okay, so let's do that quickly. So what is the formula? So ALI equal to H of ZLI and ZLI equal to WL transpose AL minus 1 I plus BL. So the first part it is the same as before. I have to take the derivative of A with respect to Z and it will give me the diagonal matrix, that's fine. Now what is the derivative of Z with respect to W? Now when I am taking derivative with respect to W is a matrix. And I have not told you the chain rule for matrix value, function that take matrices as input. Right? But I can flatten Z. I can pretend as if W is a vector. Although I am writing it like here as a matrix form, but I can just pretend it's a kind of huge vector of size D whatever ML into ML minus 1. And similarly, I have to take the derivative of Z with respect to B. So let's do the easy case first. So what is the derivative of ZL I with respect to BL? Yeah. So again, this will be a matrix. Yes, but will I get every entry in the matrix? What will happen? Okay, so let's look at it more carefully, slowly a little bit. So this is mapping what to what? What is the size of BL? ML. Okay, thank you. How about ZL? It's also ML. So this derivative would be a matrix. But does every component of Z depend on every component of B? No. So if I look at the uth component of Z, it only depends on the uth component of B. So all the off diagonal entries will again be 0. This will again be a diagonal matrix. And what will it be? Is identity. Is identity. So this is basically a diagonal identity matrix. What is the size? ML cross ML. And that's the size of the identity matrix. Okay. That was easy. How about derivative of Z, this with respect to W? So again, if you look at the uth component of Z, does it depend on every component of W? If you look at the uth component of Z, it only depends on the uth row of W. Right? So the derivative of Z, the uth component only depends on the uth row of W. So let's write it. Del of ZL UI with respect to del of WL UV, not UV. I have to use other indices. Okay, what indices? Okay, so I have to R and S, let me use R and S, okay? Because this will become a 3-dimensional matrix, a tensor it will become. But anyway, so let's do it, unfold it, okay. Yeah. So this is 0 if R, no. Yeah, when is it 0? Can somebody help me write that equation? Huh? S not equal to. Why S not equal to U? Because we are taking W transpose. Right? So that's right. Uth row of W transpose is when S equal to U. Okay? So now if S is equal to U, then what happens? Yeah. I have to do the summation, but I have to take the derivative with respect to WR. Right? Each component R. Now, yeah. So if I am taking with respect to component R, then only one term in the summation will be non-zero. And what will that be? So what will that be? A L minus 1 R I, if S equal to U. So, yeah. Right? So I can again, instead of a 3D tensor, I can just put it in a 2D form. So, yeah. So this is, yeah. So I'm done with all the rules for backpropagation now. I have computed the derivative of the ith layer, the output of the ith layer with respect to the weight vectors. This is little bit sort of, you have to think about it a little bit more. Right? Because it's a tensor, but lots of these components are zero. And with respect to a specific component, it's just A L minus 1 R I. That's sort of, yeah, repeated a little bit, right? For different values of, yeah. So it will only be non-zero for U equal to S. And then, yeah, with, yeah, so you can think of it as if, yeah. So eventually you can write this derivative in the form of a W matrix, right? Grad with respect to W. And here you will sum over all the component of zi's and then add them up. But then that will turn out to be simpler. So this I can leave as homework. Can you do it yourself? Just write the final gradient of the loss with respect to a particular layer weight. You can just write it in terms of the input and output of that layer. So AIL and AIL minus 1. In these two terms, in terms of these two, just write down the equation for, yeah. With respect to W and B. WL and BL in terms of AL and A of L minus 1. Okay. This is ungraded homework. Okay. So, you see this, okay, so when we do this, what's my picture? I have X as the input, which I can write it as A0, and then I have W1, B1, I get to A1, then I get W2, B2, I get to A2, and all the way, I go all the way till AD plus 1, and it gives me the final loss function. Okay? So that's a deep network, right? That's a deep neural network. D can be very large, in some cases 100. People have designed even bigger architectures like, many, many layers. If I take the derivative, if you remember, when I look at this term, Yeah, this is the equation I look at. Derivative of AI with respect to the previous layer. And I get this term here, which is this diagonal times WL transpose. Okay? And similarly, so basically when I do del L by del, let's say W1, I want to find the derivative with respect to first. This will be del L by del A of D plus 1 into del of A of D plus 1 over del of A D and so on up till del of A2 over del of A1. And then I do del of A1 by del of W1. Now you look at this term here, AL with respect to AL minus 1. I have these two product terms here, H of ZL and 1 minus H of ZL. So each component of this derivative is getting multiplied by these two functions. And what is my this function H? So this is Z, it's going like this. So when Z is minus infinity, it leads to 0, and when Z is plus infinity, it leads to 1. So this H is always between 0 and 1, and 1 minus H would also be between 0 and 1. And you can see that if H is 0.5, 1 minus H is 0.5, and we're multiplying these two, so it becomes 0.25. Now if Z is very large, your H could become very close to 1. If that happens, then 1 minus H becomes very small. Or if Z is very negative, then H can become very, very small. So irrespective of what values of H are, this product is going to be small. And more so if your H is in extreme. And this product gets multiplied layer by layer by layer by layer. If I want to find the derivative with respect to the first layer, then I have to compute this product for all the layers after this. Now, any entry in any of those layers, it becomes extreme, it becomes very, very large. Then my product will become very small. And even if all the entries don't become large, even if they are moderate, but then since you are multiplying them, the derivative is going to become very, very small. So therefore, any deep network, 3-layer neural network, no problems. One hidden layer, you can learn the way, it's not a problem. But the moment you try to make it a deep network, because of this product that gets accumulated over multiple layers, what happens is that the derivative of your loss with respect to the initial weights, they become very, very small. And because of which your network doesn't learn. And it's very hard to learn the weight. So that is a major problem of deep network, because of which neural networks are not successful. So earlier, when you take the derivatives, you can't learn more than 3-4 layers of networks, and therefore, we could not do much with the neural network. They were able to solve simple problems. Most of the time, support vector machines or boosting based algorithms used to do very well, until we figured out how to train these deep networks. And once that happened, then it led to a revolution. So I'll talk about some things that we look at how to solve this problem. Essentially, there are multiple ideas that come into being. There's a classical paper by Hinton where it talks about deep belief networks, how you use that to train deep networks. Also, there are a lot of papers on how to when you do gradient descent, how to choose the step size. We've done a little bit of experimentation on step size, but there are multiple methods. So that we'll talk in the subsequent lectures. And this is a recurrent problem. Any deep network, and there are no good rules how to train a deep network. You create a new architecture and you think it is great, but it will not learn. So you have to come up with a method of actually making it learn. And different people, they have come up with new architectures, but doing this learning is a very important component of it. How do you actually learn that network? How do you modify the gradient descent to actually learn? So yes, that we'll discuss next time. Are you guys now all settled? Add drop is over? Okay. So what I would suggest is, okay, I'll look at the final enrollment numbers based on this. Try to make groups. I'll tell you the group size. It will be either 3 or 4, but I'll look at the enrollment numbers based on that decide. And we are planning to release the assignments and also your reading lists. So I'll post the reading list and a tentative date when we have to present. So you can make your groups. I'll tell you the group size tomorrow, and then we'll take it forward from there. Okay. And homework, next homework, I want you to do the experimentation on the Geoflops. So I'll be posting out Moodle. I'll send out an email. Stay tuned. It will be due on before the Wednesday's class. So yeah.